Number 47, we're told to solve the equation. We have 4a squared minus 9a plus 5 equals 0. So we've got ourselves a quadratic equation here, which means at the end of all of our work we should have two solutions, a equals some number and a equals some other number. Remember, like we talked about in number 46, when you are solving a quadratic equation, you want to make sure that your equation is in standard form, meaning it's set equal to 0. If it's not set equal to 0, you have to make it set equal to 0 by moving anything that might have been here on the right-hand side over to the left-hand side and then setting your equation to 0. In this case, let's go ahead and jump right in with our factoring of the left-hand side here. So we have to ask ourselves two questions. Is there a GCF? If there is, you have to factor it out. In this case, there isn't one. So question number 2, how many terms are there? There are 3 terms, so we're going to use the scissors method. So let's take the coefficient of 4. Let's take that constant 5, put them into a t-table. Let's list all the factors of 4. 1 times 4, 2 times 2, and 5. Well, 5 is prime, so our work is pretty straightforward there. And we want to start with the factors that are closest together numerically. So let's try 2 and 2, and 1 and 5. We'll stack the 2 and the 2, we'll stack the 1 and the 5. And normally we would flip this second set of factors, but because there's a 2 and a 2 here, flipping the 1 and the 5 will yield the same result. So we're not going to do that. 2 times 5 gives us 10. 2 times 1 gives us 2. Can we get a negative 9 using a 2 and a 10? No, I don't think so. And so we know this combination doesn't work. And again, even if we flipped and tried 5 up here and 1 down here, because both of these factors are 2, we're going to get the same result. So we know that it can't be the 2 and the 2. Let's try 1 and 4 together. All right, and so we'll get rid of that. So we'll try 1 and 4. Here from the 5 column, we have no other option but to use 1 and 5. So let's try that. And if not, we'll flip this and see what happens. 1 times 5 gives us 5. 4 times 1 gives us 4. Can we get a negative 9 using a 4 and a 5 through addition? Yeah, I think we can. If we let both of these cross products be negative, negative 4 plus negative 5 is indeed negative 9. So we can let this sign bounce over. We can let this sign bounce over. Let's wrap these horizontally. And so we're using the variable a, so we'll stick in that variable a. So we have 1a minus 1, but again, we're going to get out of the habit of writing the 1 in front of our a. 4a minus 5 is our second factor. 4a minus 5. Don't forget this was set equal to 0 originally. This was an equation, so we have to solve. And now that we've got our factors, the left-hand side is in factored form, we can set each of these to 0 independently and solve. So a minus 1 equals 0, and 4a minus 5 equals 0. All right, let's go ahead and add 1. So we end up with a equals 1. Here we'll add 5 to both sides. That'll give us 4a equals 5. And if we divide by 4 on both sides, we end up with a equals 5 over 4. And there are our two solutions, a equals 1, a equals 5 over 4. And again, like we proved in number 46, you could take each of these proposed solutions, plug them in to the original equation, and verify that they are true statements that you get when you plug them in, and therefore you're proving your solutions. All right, but there's number 47, a equals 1, a equals 5 over 4.